Hi everyone, it's Matt Cicchini here. Hope everyone is doing well. I just wanted to share some of the most recent stuff the lab is doing some of these agentic workflows and kind of this idea of this future of an augmented pathologist and how we can move from the microscope into kind of a new world through using machine learning and AI. And so we're in this really exciting time as we're moving from these analog workflows with light microscopes into these truly digital worlds. But we're doing it at a time when there's this amazing amount of technology that's available. We can do amazing things with all these generative AI tools, and it really allows us to do a lot. And just like so in this image here, this is an AI generated image that I can do a lot with this. I can now turn this into a video. And so I can make this image come alive. And I can make it as if we're going from this analog world and we're zooming down and we're moving into this digital world here. And this is I couldn't do this 6 months ago. And what I'm going to show to you in this talk is just how we can use these tools and these things that are out there today to really transform the practice of pathology just by connecting the pipes with all these things together. And so just everything I'm going to show in the talk is basically using these tools. And so in my lab right now at London Health Sciences, we're not fully digital. But I'm going to showcase to you in this talk how you can do a lot without complete digitization, without any, complete infrastructure things with massive compute. Yes, you can do a lot more once you have that, but really the time is to start now, that you can start building these things with the things that you have available right now. So I have two small scanners. I have a Grundium scanner and a Forest Light Promana scanner. My compute is a computer I bought from Best Buy and a Mac Studio that sits in my office. And I don't have any software engineers that work in my lab. I've built all this kind of by myself with some of my students and with some AI tools. And I'm far from a software engineer, but I'm going to show you some of the things that you can do just kind of connecting the pipes with some of the tools that are already out there. And it's pretty amazing what you can do. And I'm going to talk a lot about agents in this talk. And there's different definitions out there. This is how I think about it. And this kind of is built upon this definition from Anthropic, which is one of the large language model companies that makes Claude. But, at the core of these agents, there's some kind of AI tool. It's typically a large language model like Claude or one of the ChatGPT models or an open source model. And instead of just taking input query text and giving you an output here, these agents can do additional things. And so they have some control over how they do that. And so they have the ability to search for more information and retrieve that and bring that into the context window. They have other tools that they can use to help solve problems that might just be a calculator. That if you ask it a math question, it can pull up a tool of a calculator and enter it in that and return the value. Or it could be a way to write Python script or some other ways to address the question. And then it has a memory function as well, so that each time it does it, it can actually learn a bit and then do it better the next time. And so, okay, well, do these things actually matter? Do they actually improve it? And I'll just show you a simple example here of just to show you that these things can help a lot. And so I just built a simple agentic flow here in this ChatGPT agent builder that you can actually access. And I just showcase here. So I've asked it a pathology question. I even spelled some of the words wrong. That if a lung cancer invades just through the internal elastic layer, how does that influence the staging? And the first thing here is it's going to run that query just through GPT-5. And then the answer you're going to see here is here. And it's actually wrong. It tells you that it upstages it to T2. And so this is an example just of that even these GPT-5 level models can still get really specific things wrong. And this kind of limits their use in a lot of these kind of sensitive medical applications. But instead, if we actually envision it as an agentic flow, where then the system actually has the ability to say, well, I need additional information on that. And so now it's actually going to retrieve information around the specifics of the staging guidelines and not just rely on the information that's in its pre-training. And you can see here, it pulls exact quotes out of the staging guidelines. And then when it then puts that back into the context window and re-answers the question, you can see that it actually gets the answer correct and actually says, no, just going through the internal elastic layer doesn't upstage it. You need to go through the other external elastic layer in order to qualify for upstaging to T2. And so this is just an example of a very simple one, but just how just adding this additional capability can really improve a lot of these systems. And I think this is an important thing for us in pathology, which I'll kind of showcase throughout this talk. The other thing I just kind of wanted to outline here is that it matters how you present the information of AI outputs to humans, and that it's not just as simple as dumping all the output of the AI and say, "Here, human, make this better." And so there's been numerous studies on this. We did a small study here that we presented at USCAP last year, where we just gave pathologists output from an agent that was doing staging, and we then gave them the pathologist reviewers with or without, and then we had a crossover, and then they reviewed again. And the AI agent does a decent job at staging these cancers. And then we had humans doing it. This was not their area of expertise. And in some cases, they saw big improvements. So some pathologists, who were doing a great job at staging these cancers, they actually improved when they were given the AI output. However, those that were actually already doing fairly well at this task, giving them the AI output actually didn't really tend to make them better. And in some cases, they actually did a little bit worse than when they were just doing it on their own. And this is a little bit, there's some bias here, right? And so the one is the automation bias. If the AI is doing a decent job at something, that it's not really effective to just give that output to the human and just say, hey, check this all just in case there's any errors. Once you do more than one of those, you have this really strong bias that comes in where it's doing a pretty good job, and it's hard to have that level of rigor to check it all and to just redo all the work yourself. And so, like, I think that the finding from here is that it matters how you give the AI context back to the human. And there really needs to be a dynamic aspect to it. It's not just as simple as dumping it all back to the human here. And so this kind of comes to our idea of this pathologist driven AI. And so we really think it's important that pathologists are the ones who are driving the development and implementation of these AI tools. And sometimes what a barrier to this is that this idea of this regulatory approval or all these regulations that govern this is, oh, we can't use this until it's FDA approved or Health Canada approved, or there's some level of regulation or something you need. And I think that that's a problem. And I think that's appropriate for some AI tools, but I think there's a lot simpler AI tools that we can and should be implementing today as lab developed tests. And like if you think of an analog of like immunohistochemistry, these are like the cytokeratin 7 and 20s of our labs that we all have as lab developed tests that we build and utilize every day as a tool to augment the abilities of a pathologist to do our work. And I think I would challenge us to reframe some of our concepts around AI to think about them in this light. How can we build tools that don't work for every lab, don't work for everything, but that each lab can build to augment our own pathologists to drive efficiency, improvement, and improve patient safety. And that's what I'm going to kind of showcase through the remainder of this talk. So let's think about a pathology workflow. It's a very linear pathway where we go from specimens, we gross them, we make some slides, we might scan them. Pathologists might order some things. Pathologists will dictate a report. And then that report goes out to clinicians. So their input is kind of specimens, our output is kind of pathology reports. We kind of think of this like a factory. And it's somewhat a very inefficient process. And I think there's a lot of things that AI can really help with this. And so the question is just, how can our little AI agents here, I'm going to use this kind of cute cartoons kind of throughout the presentation really help us. So I'm going to showcase us a number of use case scenarios of how these AI tools and things can actually really help the things that we're doing through the lab. And so let's start with a clinical challenge. And so basal cell carcinomas are a major challenge on frozen section, right? And then we'll often get these, all these margins, especially when they're on the head and neck, because these are, anatomically sensitive areas. And the surgeon wants to take out as little tissue as possible. And this, something that's bread and butter for pathology, and it seems like it should be pretty easy, but there's challenges like these hair follicles can mimic these BCC, and you're kind of under a time crunch to do these, and then for us, these were actually all done in an offsite lab, so there's another thing too that we were sending pathologists down to cabs to do these, and so could we do this better? Can we use AI and digital pathology to really help improve this? And so what we did is we built something on top of a foundation model. I won't go through all this slide here, and it's probably too much information, but just wanted to impress upon you that there's a number of these foundation models here that are increasingly coming out that are really powerful, and you can build things on top of them. They're by no ways perfect, but I think that this opens up a new way that kind of pathologists can start to build things where we don't really need to go from scratch. and that you can utilize these as your base level and then build some kind of simplified things on top of it. And so I'm going to describe to you here what we built here. The first algorithm is called Frost that was built by one of our great residents here at LHSC, Josh Del Papa. And so we took one of the foundation models. We took Virchow for the study, which is a 632 million parameter model, and we trained it on a small number of cases. We're talking about 60 cases that we trained it on, and when we tested on 50 cases, just to see how good this is. And it turns out you can do actually pretty well with it. And so in this model, we actually optimized here for sensitivity. Because in this task, this is for frozen sections. And so we want to be able to highlight to the pathologist any area that is potentially a basal cell carcinoma. And we don't want to miss any. And so we'd rather index on sensitivity rather than specificity. But still, in order to get 100% sensitivity in our validation set, we actually still had a specificity of 86%, which is quite good, I think. And it works quite well. And so here, you can see here on this tissue here, it actually highlights an area of basal cell carcinoma here. And this works, right? If you zoom down here in this area, that in fact is the basal cell carcinoma here on this last aspect here. And you can see how this could actually really help, right? So if you started looking at the tissue all from this side and then you wouldn't find it to get over here, there's a huge time savings in just saying, hey, the cancer's down there, double check and take a look, and then you're done. And it might not seem like a lot, but this probably saves you like 30 seconds to a minute. And this actually adds up, especially when you have tons of frozens. And this could mean a big difference for patients. But okay, that's great. But how do we actually get to use this into clinical practice? Because, like this is like running on a Linux system and it's great for this little research paper and blah, blah, blah. But how does this actually help patients? And so this is where our Promana scanner comes in. And so we're actually able to get this algorithm running directly on the scanner. And so it's super cool that the slide scans and the algorithm runs at the same time. So I'm just going to show you it here actually running on the scanner here. So that this is our real frozen sections that we've scanned. And we just press a button here to turn on the BCC algorithm. And then immediately it shows up here and it highlights the area with a little heat map here where the area of basal cell carcinoma is with a really high degree of sensitivity and specificity. And this is really cool. And the other really neat thing is that it's neat to be able to actually see this on this low power. And this can be a great way to involve other people around. So if the surgeon wants to come in and see the tissue, it's a real easy way to showcase them, be like, yeah, there's a little focus of BCC here. It's more on the left side or the right side or in the inferior aspect, however they've labeled it. And this can be a really powerful application of it as well, because it kind of makes the pathology come alive. And you can do more than just saying a binary yes or no, whether the margin's positive. You can kind of give a sense of the general amount of involvement for it. And this is just some kind of example cases here. So obvious cases, it's pretty obvious here. I think there's less value in these really truly obvious cases of highlighting it, but this is the case that I think is really helpful. And so this here has tons of hair follicles here, right? Where it can be easy, you're hunting all around there, but it actually found a little tiny focus of BCC just right there, and these are the cases it helps with, right? Where you're hunting through all the tissue for that little focus in amongst all these hair follicles and everything. And there's a chance that you might miss it. Whereas this, if it just brings your attention there, it can really help and increase your efficiency for doing these things. And then it also shows to the surgeon as well, like, oh yeah, it's positive, but it's just a little bit here on this one side, versus these kind of have these large elements of tumor on them. And this can help drive their decision-making process as well. And because you're running on a scanner, they can see it in real time, which is actually quite a cool aspect of doing this. It's not something you need to send to the cloud and do all these things. This runs directly on the scanner, utilizes the edge compute on the scanner and the kind of empty GPU space on the scanner, which I think is a huge unlock that we'll see more and more of. And so we validated this on the scanner as well, and it basically continued to have a sensitivity of 100%. Specificity in the smaller validation cohort was around 90%. I just want to show you, this is the case that it actually highlighted as a false positive. But honestly, I think I would want to double check this. And this is, to me, the algorithm is actually working perfectly here, because this is something that I wanted to flag, because this is something that I might think about a little bit deeper, or maybe I'll do some additional levels to make sure there's not really a little bit of a BCC that's coming up there. And then the other thing is here is that I didn't do a crazy validation here. I kind of followed this kind of validation that you use for an IHC test, where you don't need a ton of things. So we did a larger study to show that this, and then we just kind of did an on-device validation for this. And then I think this is a level that is appropriate for use. There's not a lot of guidelines here on exactly what you need, but because this is not giving the answer and how we're reporting it, this is just an augment to me that if it's negative, I still need to look at all the tissue. I'm still responsible for it all. Its real value is just to highlight areas that I should look at and to help me to focus down my attention on areas that are positive, because once I found the positive area, I can move on. And so this is kind of what I'm getting into this idea of pathologist-driven AI tools. Is that I think this is how we have to think about this. This is not a tool that works for every lab. This is a tool that works for my lab with my IHC level and in this one specific scanner, right? And it wasn't a monumentous effort to get this validated and used. And so I would challenge us to think through these things and then start using them, right? And that we should be building these, validating them, and getting them going. Yes, you still need to do some QC and quality assurance as you're doing this, and running controls through them, positive and negative, to make sure there's not a drift in your H&E variation that's changing it. But I think we need to lower the barrier for some of these getting into clinical practice. And so along those lines is that it was still kind of hard to build this algorithm, right? We needed to do some things in a Linux environment. We needed to go on the command line and write all these things. And honestly, that's a barrier to a lot of pathologists getting involved in this, right? Is that they're not going to want to do that, like not going to want to write a bunch of Python scripts and we're all busy. We don't have the time for that, but we all want to use these things. And so what I did is I built a little application here that I called PathSeek that basically just allows pathologists to build, train, and utilize algorithms built on these foundation models without having to run Linux or write anything on the command line or anything like that. You can just click some things and it all works on the back end. And it's actually works pretty good, which I'll show you. And so I've embedded a few different models that run the VerCal model, run the GigaPath model, and I have the Uni model in there as well. And so there's a lot of applications for this. Like you could be using this to find all your cases of cancer in the backlog. And this is like a really low risk application, right? Like this is just a triaging thing, right? Like can it just find cancer of cases that are waiting to be signed out and put those to the top of the queue, right? Like I really think there's you don't need a real high degree of validation or for this because it's just triaging, right? If it misses some, like that's okay. It's still for every case that it does get right, though, that helps just triage things more appropriately. And you can iteratively improve on this. This is a very safe place for this. And that's where I think a lot of the initial things we should think of for these AI agents and algorithms is really in this initial QA aspect of it. It's not really from a diagnostic perspective, but just helping us automate some of these other things that take a lot of time. And so this is what the program looks like here. And so it's pretty simple to use. You just tell it. So this is set up there's a few different modes of it. This is the rare element detection mode. And so you just give it a few examples here of what you want it to find here on the slide. And so in this case here, there's a signet ring tumor here that's involving these lymph nodes. So I've given it a few different examples and I basically extract embedding. So it's going to run VerCal on the back end. It's not the fastest because it's just running on my Mac in my office. So I sped it up for a little bit for time. But then you just train the detectors here on it, and then it will actually then run the detection here on the slide here. And I'm just going to show you, jump ahead here. And so you can see this is what the output looks like. And so all these blue tiles here are areas that doesn't have tumor in it, which here's just negative node. But you can see here the areas that are red tile are high probability of having cancer in them. And then you zoom down, and then these are the actual areas of signet ring tumor cells involving the lymph node here. And so, and I built this in my office just as I was looking at this case. And so I didn't need some giant, supercluster or massive training set. I just built this as I was going through this case, and it helped me solve my problem, right? I just wanted to showcase the distribution of the tumor that looked like this on this slide or the other slides in this case. And it can be a really effective way to move through it relatively quickly and do some interesting things. It has different modes. It has a classifier mode that I built too, so you can give it different components here. So here I trained it on the benign epithelium, some of the background stroma as well, and then the tumor here. And then you can see that it does a pretty good job of classifying these different components. And then I can then apply this to a different slide. And so this is a different slide here where it actually is picking up the cancer and then the background uninvolved mucosa as well. And so with these tools, you can kind of build things pretty quickly. It's like, I think last week I kind of trained 5 different algorithms just as kind of working through cases in my office. And it kind of opens up this new way of thinking about cases, right? Of like, just like, I want to show me everything on the slide that looks like this. And these are things that were not really possible, without these tools, right? And it can be really practically useful. And so this is an example here. I just took this TCGA case here and there's a squame, and I just wanted to show all the nerves. And so I built a little simple thing here, just gave a few examples of what the nerve looked like. And then it goes and finds the rest of the nerves on the slide. And it does a pretty good job of finding all these nerves on the slide, right? And you can and this can be really helpful. Like imagine you're hunting for perineural invasion and you can just click a few buttons and then all the nerves actually now show up on the slide. And then you can better identify the area that has perineural invasion. Like this can be really powerful. And you can just build this and run this on the fly. And in fact, here I actually classified all the different cellular components with red of tumor and some of the muscle and things on the slide. And so there's lots of ways that you kind of build it. And these things have a fair bit of power of what they can do. But then you can do like really esoteric things too. Like I'm a pulmonary pathologist, and one of my interests is interstitial lung disease. And so in ILD, we have these things called fibroblastic foci here, which is kind of these loose proliferation of fibroblasts. And I'm pretty sure no AI company is ever going to build a tool to find AI fibroblasts for me that's going to get FDA approval. But like with this kind of PASSIC thing, I can give it a few examples, and now suddenly it's now with really good accuracy actually highlighting all the fibroblastic foci on a slide here for me. And so I can do things like say, like, okay, well, what's the distribution of these? Can you enumerate these? Where are these located on the slide? And and these are things that weren't possible without these tools. And I didn't develop some crazy model and have to train on a ton of slides. Like I trained on one slide, give it a few examples, and then it works. And then you can see these things. Like, it's a different way of thinking about these AI tools, right? This is like an AI on the fly. This is a tool like that I can use in my practice and have this flexibility and this freedom to just do things. It's a sandbox in which I can control these AI tools. And then, like, this is another example of that. You can give it a few examples of what a granuloma looks like and say, show me the distribution of all the granulomas on the slide. And so in this case of sarcoidosis, I think you can nicely see the kind of distribution of these granulomas. And this can be really helpful for trainees who are looking at the case, right? To explain to them, what's a lymphangitic distribution of granulomas falling along the bronchovascular bundles and kind of subpleural location as is kind of this idea of this lymphangitic distribution, which you can kind of see beautifully at this low power image here once you highlight them, which you wouldn't really be able to see if they had to zoom into higher power. You kind of lose it, right? And so this just opens up new ways in which we can look at these things. So that's great, but like one thing I hate is like annotating slides, and so when we want to do this on larger aspects, how do we get more and more label data in a more efficient way? And this is something that my lab and I've thought a lot about, and we have some different ways of thinking about how to do this. And one way, we've done some social learning ways of doing this. And so we did this large mitotic figure project where I think it's actually still the largest database of mitotic figures. So we had 1,000 mitotic figures with 85 pathologists from around the globe that actually scored them all as being a mitotic figure or not. And then we got some really cool data. Like we had all these 1,000 mitotic figures, and then everyone voted on them whether they actually thought they were a mitotic figure or not. So we have an 85 pathologist consensus on each one of these images here. And so you see things here like the top panels here that these are high confidence mitotic figures, and I think these are all things that we would agree with as being mitotic figures. But things on the bottom here that other people called mitotic figures, probably aren't mitotic figures, right? Or maybe they are, but these are less confidence. And so the cool thing is that we now have this data set that's not just classified as a binary yes or no mitotic figure, but it has this strength of the signal, and that we have the confidence of like how many pathologists would call this a mitotic figure. And this can be really helpful, right, in building these new data sets. And a number of people have used this data set in additional studies to the test against and to help build their own systems. And we generated this really quickly just from this kind of social study where we got pathologists that we connected with over social media, and then got them to be part of the study. We used open source data, and then we had them scored, and then we suddenly had the largest consensus study of mitotic figures in the world, which I think is can be really powerful. And then we built this into a little training app here, where now so we give this to a lot of our trainees, where they can actually see these little tiles and then say, whether it's mitotic figure or not. Because the one thing is that we never actually train people on is like, are what they seeing mitotic figures or not, right? People typically just do counts on their own, and then the pathologist will then count maybe a different field, and then if they're around the same, we just assume they're doing a good job, right? But this way, you can kind of get do this a little bit more dynamic way, and we've done this too with now PDL1. So in collaboration with Diadeep, we have a new PDL1 trainer app where you can kind of do the same thing where you can get these tiles and you can score them, and then you can kind of see results. But the cool thing about it is what I really like, is that after you do it, you see your distribution of scores, and then you see the distribution of everyone else who has been doing this here. And it's got a bit of a gamification aspect to it. But I find that this part is really useful because I can see, like, am I like scoring too high? Am I scoring too low? Or am I kind of with the distribution of my peers? And so I think that that can be a really powerful aspect here of just getting a sense of kind of where you are on this. And because you're doing this on these kind of small tiles, you can do it really quickly. And so this is a really efficient way to be able to get these scoring aspects here. Another cool way to get the data is kind of using eye tracking here. And so we've set up here with one of my grad students, Elena Lopez, looking at using eye tracking here for getting pathologist gaze when we do a number of tasks. And it's actually pretty cool. And so like you can have this case here where I'm like searching for my target figure. And you can actually see how my gaze actually goes as I'm searching for this across the slide. And then once you find it, you kind of see how the gaze kind of fixates around it. But it can kind of be a way of getting labeling data without requiring me to annotate anything or to put circles around anything. And it can be a real powerful new way of doing it. And we've even done some things where you can actually move the slide around with your head and kind of eye gaze, which is kind of fun and interesting way. But so when we were developing the system, we actually needed a way to pilot it and get it optimized before we had all the REB in place to use actual tissue. So we needed a little optimization study. So we decided to use Where's Waldo images from it, and we actually found that it was actually so interesting. We actually turned it into a little bit of a study here, where that we actually got published, where we looked at pathologists and non-pathologists and their ability to find Waldo on an image, which kind of recapitulates a search task that pathologists normally do, right? Of like whether I'm looking for mitotic figure, tumor and lymph node, or where's Waldo. And we found an interesting thing here. So I'll first show you the non-pathologists here as they go through it. So as they look, it's kind of like chaos. It's kind of like everywhere. The search pattern is kind of really haphazard. And then the size of these dots are basically how long did they fixate on it. And then the lines are kind of their saccades as their eyes move. So if you contrast that here with the pathologists, they have really this organized, grid-based way of doing it, and then the eyes are actually moving much faster, and then the size of these dots are actually significantly smaller, and that our fixations are shorter. And so the pathologists have a much more kind of grid-based way of looking for it, and then our eyes actually have shorter fixations and quicker saccades as we're kind of moving through this aspect here. The other really interesting thing here is that we compared pathologists looking for a pathology specific thing like mitotic figure and Waldo, which is like a non-pathology item here. And then when finding Waldo, pathologists actually had to typically foveate over it to see it. And so these five of these arrows are just the saccades before and after finding the target here, whether it's for a Waldo or mitotic figure. And you can see here in the Waldo search, actually the saccade jump is actually largely within this foveated vision area. Whereas for the mitotic figures, we saw these big jumps, which really supports the fact that we're actually seeing these here in our peripheral vision, right? That we spot it, and then we have this jump as our eyes then move and saccade over, and then fixate on on the target of interest. And so it's an interesting thing. And I think we all realize this in our practice. I think we've all been that trainee when you're sitting down at the scope with a really experienced pathologist and you tell them that, oh, there's no mitotic figures in this area. And they say, oh, it's right there. And I think we've all had the experience where we've just been really amazed at the ability of pathologists to do this. And I think this data supports that we actually have the ability to perceive these aspects in our peripheral vision. And we're thinking about exploring this in some trainees and to kind of ask the question of like, when do people get this ability? Like how long does it take to do this? And you can also do things like in the study here, we looked at window size and to say like, well, where do pathologists foveate on in the window here? And that we found that when pathologists kind of have really large windows here, they tend not to foveate their vision on the periphery here. Which could conceivably be a problem. In this study, we actually had them try and find lymph nodes, tumor lymph nodes in different size windows, and we didn't really see any different success. But there is a theoretical risk that you could be missing things on the periphery of your screen here, that where your vision is not really typically foveating over this. And so it's something to keep in mind if that you're doing pathology on a very large monitor, that you may not be perceiving the outer aspects of the screen. And so if you're doing things like a comprehensive search task, like looking for tumor and lymph nodes, you may want to overlap your fields if you're using the entire screen, just to realize that you may have a limited aspect to actually be truly assessing the outer aspects of the field here. So just something to keep in mind here while you're doing these slides. Another thing that I spend a lot of time doing is actually like reviewing my reports. I spend a lot of time making sure there's not a transcriptional error or some other kind of logical error in my report. And this actually like takes up a large part of my day, is actually just making sure my text to speech software didn't put any kind of crazy words in there. This is kind of a big point of stress for me of like, did I make a typo or something else in the report? Because it's relatively easy to do, especially with these speech to text programs can actually like write words that sound like the word you're trying to say, but really don't make sense in that context. And I think this is a space where large language models can really help. And so I realized this, and I tried putting some synthetic, so not real patient data, into these ChatGPT models, and I found that they were really good at like picking up errors and typos and things that just didn't make logical sense. But the problem is that you can't actually put patient information into just dumping into ChatGPT, right? And so what we did is we actually, this is where I use my Mac Studio again. We actually utilize it to put content. Yeah, we actually use the Mac Studio, and we run the models locally. And the advantage of that is because the Mac Studio lives in my office, the data is not going anywhere. And I can use these large language models for things that with sensitive information like personal health information, because it's locally implemented within the hospital firewall. And so this can be a really safe and practical way to implement these and kind of improve efficiency and workflows. And so to kind of test this out, we did kind of a prospective study where we actually took a number of cases that we ran through. And just as a way to check for typos. And so this is an example here. And this is just running locally on the computer here. And then in this case here, it actually identified that there was an error here in this case where I had actually listed it as well differentiated in one spot, but moderately differentiated in another spot. And so this is kind of an area that could generate confusion. And so other examples we had was in some cases it actually like there was like sound alike words, like I think we had a follicular nodular design instead of follicular nodular disease in places. And so these type of typos, these models are actually pretty good at picking up. And some of these are actually ones that it's kind of hard for the human eye to actually perceive. Like it's easy to kind of overlook the follicular nodular design versus follicular nodular disease. Well, the thing is that these models can be really good at performing a way of getting uniform kind of workload measures out of cases. And so, you know, often sometimes the problem with workload measures is it requires pathologists to kind of input specific data or calculate things on their own, which can actually take time. And also sometimes people will kind of like differentially apply some of these rules, and you can kind of get some lack of uniformity in this. And so we kind of just built a system here where we can actually just dump in pathology reports, and it'll actually pull out L4E, which is the workload measure that we use here in Canada for these different cases. So this can be a really powerful thing here where you can actually just get these workload measures instantaneously without requiring pathology time, and it does it really in a uniform way. And so just kind of end on some fun stuff here that I think the other great place for a lot of these tools is in pathology education. So I was very fortunate to be part of a kind of a great group of pathologists who put out this paper here, and we kind of like highlighted a number of ways in which you can utilize these things to help improve education. And I really encourage you to take a look at this because it's going to be really there's a lot of really great use cases here in the education space, but just wanted to showcase some of the more recent stuff we've done, which I've also posted on social media here, which is kind of fun. And so I had to do a lecture for the residents here on some molecular pathology things, and so instead of actually just giving them kind of a dry didactic lecture, I decided to make some games here. And here, this is basically an example of I made a Pac-Man game here where you have to actually match the Pac-Man with the ghost that is the fusion. So that was EML4 and ALK, and then here we have EGFR. Then you have to try and match that the mutation here is L858R. And then the cool thing is then you learn something as you're doing it. So once you find the correct one, it'll actually give you a little thing about this fusion or this mutation and tell you a bit about it. And so it's a way of kind of getting at this rote memorization thing and making it a little more fun and interactive. So just looking at this, I can be looking at, okay, Matt, okay, that's exon 14 skipping. I got to try and find that, and it's a kind of way to make it a little more interactive and fun. If you're more of a Space Invaders fan, I also made a Space Invaders game here where, you're a sarcoma here and you have to try and find the fusion that connects with it. And then once you hit the right one, it then tells you a little bit about it. So this is kind of just a way to kind of make learning fun and interesting. But the cool thing is that I actually built this just by talking to an AI tool. So this is just with Claude and Anthropic, and I just basically described what I wanted and gave it some of the content, and then it made this whole game in a playable way. And so that QR code will actually bring it to a link where you can play it. It works best on a computer, but you can actually it actually just makes it come alive. And so like both these games took me less than 15 minutes to actually generate. And it's just by simply talking to Claude on Anthropic that I was able to actually make these and get these running. Jason Wasserman developed this amazing website called mypathologyreport.com, and he's truly an inspiration. And I'm really inspired by everything he does, and that he's built this website from nothing, and with truly just the goal of helping patients better understand the pathology report. And it's every article on the site is actually written by pathologists and reviewed by patients, and it's truly this world class resource that he has, tens of thousands of people looking at every single day. So patients all around the globe are actually using this to better understand their pathology report. And they're actually sending in questions, but we don't really have the means in the site because it's really just Jason to do this. And so Jason and I collaborated on, can we use large language models to help solve this? And so we had a great medical student, Will here, who actually helped us integrate a large language model directly into the website. And so we made a little name for him. It was like, he's Osler here, our AI assistant. And you just ask Osler questions. And so the idea here is that we're just launching this right now. And that's so Osler will be able to respond to questions. And it uses the content from my pathology report in the answers. And it will actually cite the answers here. So you can ask questions like what's an adenocarcinoma of the lung? And then it actually gives you the answer here and describes it in a way in which a patient can understand. And then it actually will cite the additional resources where it got it from. So if the patient wants to know more about it, they can click on the link and learn more about it and kind of dive deeper. And so it's a way that we can kind of make this information come alive and really help patients better understand their pathology report, which I think is hugely important. So I hope you enjoyed this talk and kind of showcase some of these ways in which we can start putting some of these agents into these workflows. But I really don't have all the answers. Really, this is just kind of the start of this all, right? Like, I'm just showing you some of the pieces of the puzzle that we can start fitting into here. And I really think the next challenge is really orchestrating these things all together, right? So, like, I've shown you how you can kind of build things and some of the building blocks, but like, well, then how do you orchestrate these together to really generate these efficiencies? Like, can you have an AI agent that pre-screens all your GI biopsies and finds all the cancer and brings those to the front of the line, or to pre-order stains on certain things, right? So I think that is the next key challenge and thing we need to do. That we have some of these capabilities now, but how do we put these all together in order to build these truly agentic workflows that I think can really transform pathology? And so, like, I think these are some of the things that were going to be possible within a few years, right? Like, I could be looking at a case like an ILD case and be able to say things like, fibrosis in this seems a little bit odd. Can you like highlight the distribution? Because it doesn't really fit like a normal pattern. And then this might trigger an agentic flow that then first cross-references the literature. It's after it's highlighted the pattern, and then it can then, and if we have all our slides scanned, then it can then search back through this and say, have we seen this distribution before? And then maybe it has. Maybe we have a cohort of 30 patients who have this kind of distribution. And then if it has the ability to mine information from the medical records, it could then start pulling out the histories and outcomes, and then you could kind of be defining a new presentation of disease, just from an observation of your microscope. And so like this is the future that I hope for us, is that that we're in the driver's seat of controlling these agents and these things, and such that it empowers us to do things that are not really possible right now, right? That you can take these insights that we all get as we're sitting down in the microscope to not only just allow us to do our current job better, but to allow us to do things that are not possible right now, to better understand disease with every case, right? And to be this kind of window and these tools that really can bring us to new aspects. And so with that, I just wanted to close here and hopefully you enjoyed this. And please feel free to reach out. And I hope for a bright future where we all can work in collaboration with a number of these agents to really not be black boxes that replace us, but really things that can kind of augment us as pathologists and bring us into this next level and allow us to do amazing things that are not possible right now. We really haven't solved all of pathology and medicine, right? And so it's not just can we do this cheaper and faster, but how can we all work together in a synergistic way to do this all better? So thanks everyone and have a great day.